Good morning, girls. So we begin our today's session for now. The winners of the question which was asked yesterday, answer was given correctly by Savina, Swati, Usha, Anita, Arshia, and Jennifer. So congratulations to all the girls who have given the right answers. The others also have given it right, but we are taking the first quick answers to be displayed. So congratulations to all of them who answered fast. So today's class, we will be seeing about what are capacitance, what is the expression for capacitance of a parallel plate capacitor, and how capacitors are connected in series as well as in parallel. So we are going to study these three things today. See, I will be showing you two slides. One is from the textbook, directly how we write it. The second one is for the animation thing, just for you to have a better understanding of the concept. So when you are writing in notes, please put down what is given to you in the white paper. Now what you can see, the same screen notes can be put on the book when you're writing your notes. I will be displaying something like this in blue. This is just for your understanding. The same thing is repeated. So for notes, please write down what is in the white paper. Clear? So we are deriving an expression for capacitance of a parallel plate capacitor. Now what is a capacitor? You know, it is used to store charges. And you have two parallel plates here. One plate is on top, the other plate is down. I'm labeling it as 1 and 2. So these are parallel to each other, hence we call them as parallel plate capacitors. And you can see clearly, positive charges are placed on the first plate, negative charges are placed on the second plate, and there's a gap in between them. So we call that gap as the medium, which is here. So you can see electric field is acting in the downward direction. The distance between the plates A and B is given by the letter D, and area of each plate is given by the letter A. Surface charge density on the plate B is minus sigma, and surface charge density on the plate A is plus sigma, because we have positive charges here and we have negative charges. So that will be your diagram. Two parallel plates you will write, label them as A and B, or you can write it as 1 and 2. On the first plate, put all positive charges. On the second plate, put all negative charges. Distance between the two plates, you label it as D. And area of each plate will be denoted by the symbol capital A. So to begin our derivation, after drawing your diagram, you have to just mention the electric intensity between the plates. Between the two plates is given by capital E equals sigma divided by epsilon naught. So this is our formula. E equals 1 by epsilon naught times your charge. That is your law in electrostatics, Gauss law in electrostatics. So keeping that, E will be equal to sigma divided by epsilon naught. Sigma is your surface charge density. And for surface charge density, we have a formula. Sigma equals Q divided by A. Q is the total charge and A will be your area of cross section. So first formula what we did, E equals sigma divided by epsilon naught. Now what you have to do is, sigma value we have Q divided by A. So substitute that here. Observe carefully. E equals, in place of sigma, you have to write it as Q divided by A. Along with that, in the denominator, you have epsilon naught. Clear? First formula is E equals sigma divided by epsilon naught. But sigma is equal to Q by A. So you will write E equals Q divided by A into epsilon naught. Call that as equation 1. We have E equals V divided by D. That is in terms of your potential difference. This is the formula. E equals V divided by D, where V is the potential difference between the plates. Call that as equation 2. Now comparing equations 1 and 2, left hand side we have E. So I can equate my right hand side. What will I write? Q divided by A epsilon naught will be equal to V divided by D. So you're going to equate equation 1 and 2. Cross multiply, what will you get? I want this V down to the denominator, and A and epsilon naught will go up to the numerator. So we will get Q divided by V is equal to, when this goes on top, it is epsilon naught A divided by D. I can write it as A into epsilon naught or epsilon naught into A divided by D. Now, by definition for capacitance, C is nothing but Q divided by V, that is charge divided by potential. So in place of Q by V, replace it with C. This equation of Q by V will be replaced with C. So C will be equal to epsilon naught A divided by D. This is our required expression for capacitance of parallel plate capacitor. So just go through it once more. Those were joined late. From tomorrow, I'm locking the meeting. If you are on late, you will not be allowed inside. Today will be the last chance for those who are coming late. The electric intensity between the plates will be given by capital E is equal to sigma divided by epsilon naught. This is our general formula. Sigma will be equal to Q divided by A. Substitute here. So in place of sigma, write it as Q by A into epsilon naught, what is already there in the denominator. Call that as equation 1. Second definition we have, WKT is, we know that E is equal to V by B, where V is the potential difference between the plates. Now compare equations 1 and 2. Q divided by A into epsilon naught will be equal to V divided by D. Rearranging, V will come down to the denominator, A into epsilon naught will go up to the numerator. So Q by V is equal to A into epsilon naught divided by D. For reference, I'm just rearranging it and writing epsilon naught into A divided by D. By definition, Q by V is nothing but the capacitance C. Therefore, C equals epsilon naught A divided by D. This is the expression for parallel plate capacitor with air, AIR, air as the dielectric. Now, when we have any medium, there's only one difference. This epsilon naught will again be multiplied by epsilon R. Epsilon R is the permittivity of the medium. So my formula will become C is equal to epsilon naught, epsilon R, capital A divided by D, if it is medium instead of air. So the same derivation can also be proven like this. If you want the definition for a parallel plate capacitor, it is the arrangement of two parallel conducting plates of equal area separated by air. That is what we saw now, or any other insulating medium. We can have a paper in between, or we can have mica. Mica is a material like a sheet, or you can have glass, or you can have wood, ceramic, or anything else. But for our explanation, we take air as your medium. Now you can see the diagram here. What you saw there, the two plates on top and down, is explained to you simultaneously. See, you can see the diagram here. This is plate 1 and plate 2. Now in this diagram, this is plate 1 and this is plate 2. I'm showing it to you vertically. So you can see clearly plate 1 is having only positive charges. Plate 2 is having only negative charges. So surface density here will be plus sigma, and for the second plate, which is LO, will be minus sigma. And area of cross section is capital A. We are separated by a distance of D. And you can see the electric field is denoted by the symbol capital E. Now for our formula, first formula what we did, E equals sigma divided by epsilon naught. Second formula we saw, E equals V divided by D. When you compare both, the third expression, what I showed there was V is equal to Q by A into D into epsilon naught. But C equals Q by V. So what you will do here is C will be equal to A into epsilon naught divided by D. You will rearrange this term. For V, you will substitute it here. C equals Q divided by V. But what is V here? QD divided by A into epsilon naught. Q and Q will get cancelled. We will get C is equal to A into epsilon naught divided by D. If the space between the plates is filled with dielectric medium, then C is equal to A into epsilon naught into epsilon R divided by D. So this is the dielectric constant if your medium epsilon R is introduced. This capacitance of a parallel plate capacitor will be directly proportional to the area of the plates, which is on top, numerator, and it will be inversely proportional to the distance of separation between the plates. So seeing your formula, you can write C is directly proportional to A and C is inversely proportional to D. Now, having completed this, the next question we are going to see is, we'll have a derivation for equivalent capacitance of two capacitors connected in series. Be very careful when you draw your diagram. There should be two equal parallel lines. If you draw one line little bigger, it will become a cell instead of a capacitor. So here you have to mention two equal and parallel lines. As you can observe here, name the first combination as C1. The second combination will be C2. The charge on both the capacitors will be Q, and the potential on the first capacitor will be V1, and on the second capacitor we will write it as V2. For the combination, the total potential is V. Now, current electricity chapter we did derivation for resistors connected in series. So how they are connected in series? One end to the other end. If they are connected like this in a straight line, see, only one terminal will be connected. We have two plates here. So like standing in a row, if you connect them, then we call it as series connection. Parallel means both the ends have to be connected. Series means only one end to end connection will be there. Parallel combination means both the ends have to be connected. So you can see here clearly only one end of C1 and C2 are connected. The other ends are connected to the common voltage. So this combination is series combination of capacitors. You have one equivalent capacitor here. What is equivalent capacitance is? It will give us the same effect as the combination. Now if C1 is 1, C2 is 2. Add both means I will get 3. CS can have an output of 3. So any single capacitor which gives the output as the same of the combination, we call it as equivalent capacitance. Since we are connecting in series, I will label it as CS. If it is connected in parallel, you will label it as CP. So here, two capacitors C1 and C2, equivalent capacitance is CS. Common potential is V. Common charge is Q. V1 is the potential across C1 and V2 is the potential across C2. This is the description of your diagram. Now when we go to derive, the total potential in figure 1, V, should be equal to V1 plus V2 because there are two capacitors. But we have a definition, C equals Q by V. That's a definition for capacitance. You rearrange it, you will get V equals Q by C. So when you do this, for the first capacitor, V1 will be equal to Q divided by C1. What will be V2? Q divided by C2. Now add both. V is equal to V1 plus V2. So V will be equal to Q divided by C1 plus Q divided by C2. Take out Q common. What do you get here? 1 divided by C1 plus 1 divided by C2. Call this as equation 2. I'm telling you again. Commonly we take V is equal to V1 plus V2. Formula is V1 is equal to Q by C1, V2 is equal to Q by C2. Add both, common terms are Q. Take that out. You'll get 1 by C1 plus 1 divided by C2. Call this as equation 2. If Cs is the equivalent capacitance in your second diagram, then V equals Q divided by Cs. Call this as equation 3. From equations 2 and 3, what can you get? V and V are common. So I can write Q divided by Cs is equal to Q into 1 by C1 plus 1 by C2. What is common in both the terms? Q. So you can cancel them out. When you cancel them, you will get 1 by Cs is equal to 1 by C1 plus 1 divided by C2. This is our expected derivation. So if you're writing it in statement, the reciprocal of the effective resistance will be equal to the sum of the reciprocal of your individual resistances. That is in terms of capacitors connected in series. So I think you're clear with it. Two capacitors you keep. Total potential V will be equal to V1 plus V2. Substitute the formula. V1 is equal to Q by C1, some definition of capacitance. Then V2 will be equal to Q divided by C2. Add both, take out Q common, 1 by C1 plus 1 by C2 will be given as second equation. Replace the combination by a single capacitor whose equivalent capacitance is Cs. Then V will be equal to Q divided by Cs. From equations 2 and 3, Q by C1 will be equal to Q into 1 by C1 plus 1 by C2. Cancelling of the common term Q on both the sides, 1 by Cs will be equal to 1 by C1 plus 1 by C2. I want you to write this down onto your notes. Expression for two capacitors connected in series. The same thing, I'm repeating it again. So we have two capacitors. You can see the pink dot here. That is where we can see how the capacitors are connected. They are the terminals of your capacitor. So you can see C1 and C2, only one end is connected. And the next term will be connected to your, here we are taking three capacitors. You can have n number of capacitors and connect them to a common voltage. So one side will be plus, the other side will be minus. Last example I've shown you for two capacitors connected in series. Here there are three capacitors. You can add n number of capacitors. Now in series combination, charge is same. Please mark this as a point in your book. Charge will be same on all the capacitor. Potential will be distributed in inverse proportion to capacitances. That's why we write it as V1, V2 and V3. But charge, everywhere you write it as Q, Q and Q. So in series combination, charge will be same on each capacitor and potential will be distributed. So you can see in the diagram, Q is common, potential is written as V1, V2 and V3. Those who know the answer can just lift your hand. We are taking three expressions now. V is equal to V1 plus V2 plus V3. What is the expression for V1? Last derivation, what we did. V1 equals, Pavishri. How to write V1? Yes,
Q
Kavishri.
by C1, ma'am.
Very good.
Q by
Q
C1.
divided by C1. What is V2?
Q by C2.
Very good. V3?
Q by C3, ma'am.
Very good, Kavishri. So we write it as Q by C1, Q by C2 and Q by C3. This is the general formula we have. V is equal to Q by C. So you substitute it as Q by C1, Q by C2 and Q by C3. So when you do it here, what is common? I want Josefa to answer. What is common in this expression? Or anybody who knows, just raise your hand. Yes, Jennifer. What is common? Preeti N.
Q, ma'am.
Q is common. So if you remove out Q, what will you get? How can I write it? I'm removing a Q common. So what will be my expression?
1
1
by
by
C1
plus.
plus 1 by C2
Hmm.
plus 1 by C3.
Very good, Preeti. So if you take out Q common, you will get 1 by C1 plus 1 by C2 plus 1 by C3. Since the equivalent capacitance is 1 by C here, this is our final expression. Instead of writing CS, you can just write it as C. So this is how you have to do your derivation for series combination. Now if there are n number of cells, then we can write a sigma notation. Sigma notation means we are adding up. So you will write it in statement form. The reciprocal of the effective capacitance is the sum of the reciprocal of the individual capacitances. Have a book and paper in your hand. We'll see if you're able to derive it for parallel combination. So derive an expression for equivalent capacitance of two capacitors connected in parallel. So you can see here both the ends of C1 and both the ends of C2 are interconnected, or one is on top and the other one is down. So we call this as parallel combination. Series you saw only one end was connected, but here you can see two ends will be connected. Both the ends will be connected. And you look at the charge here, it is Q1 and Q2, whereas potential is common, V and V. So that is the difference. In series combination, charge will be constant, potential will change. In parallel combination, charge will change and potential will remain constant. Now, when we took series combination, how did we type the formula? V is equal to V1 plus V2 because potential was changing. But here you see what is changing is your charge. So we will write Q is equal to Q1 plus Q2. Understood? So series when you take, we will start with V is equal to V1 plus V2. Parallel combination when we take, Q should be equal to Q1 plus Q2. I want you to do it in your book. The charge on the first capacitor. See, our formula for capacitance is C equals Q divided by V. So if I want Q, I can cross multiply C and V. So what will I get? Q is equal to C into V. That is my general formula. So Q1 will be equal to C1 into V. V is common. Q2 will be equal to C2 into V. Now, substituted in equation 1, Q will be equal to, in place of Q1, write C1V. Please do it in your book. Plus C2 into V. What is common here? V is common. Take that out. You will get C1 plus C2. Call this as equation 2. Now, if Cp is the effective capacitance, see the second diagram. Here, Cp is your effective capacitance. Then again, Q will be equal to Cp multiplied by V. Call this as equation 3. Now, compare equation 2 and 3. Left hand side is Q and Q. So, equate your right hand side. Cp into V will be equal to V into C1 plus C2. What is common on both the sides? Cancel out V and V. So when you cancel out V and V, you will get Cp is equal to C1 plus C2. So this is our expression for parallel combination. One point to just keep in mind is the formula for capacitance. That is C equals Q by V. So if I want Q there, cross multiply C into V. And in parallel, voltage remains same and charge is changing. So the first expression will become Q1 is equal to C1 into V and Q2 will be equal to C2 into V. Now just raise your hands. How many of you were able to do this derivation? Kavishri, yes. Sneha Purushottam, Dhanalakshmi, very good. Swati, Monusha Evangeline, Reenu, Dhanalakshmi, Usha. So majority of you are able to follow it up. So this is how you have to do it for series as well as for parallel. Very good. I'm happy that almost all of them, Nancy, Komala, Vishalakshi, Hussefa, Priscilla, Kirtana, Sanya. So everybody is getting the answers. Very good that you are able to do it. We'll just see the diagram once. So if you are connecting in parallel, almost 28 of them have raised their hands. Good. So we are connecting two capacitors in parallel. Pink color dot is the two terminal. Observe carefully. C1 and C2. Now you can see three capacitors we are taking. So they will have three terminals. Look at the line joining. All the 3 points are getting connected, or both the ends of the capacitors are connected to a common point. So this is how parallel will be connected. Series you saw only one pink dot to one pink dot was connected. Here you can see both the ends are connected and we replace it to a common potential. Now in parallel combination, what is same? Potential will remain same across each capacitor and charge will be distributed. Charge will be distributed which is directly proportional. See, last in series, no, I told you potential is distributed which is inversely proportional. That is why we had the formula 1 by C1 is equal to 1 by C1 plus 1 by C2. Here if you see, no, directly proportional, you will get C is equal to C1 plus C2. Just remember, potential is same and charge is distributed. So we do our derivation like Q equals Q1 plus Q2 plus Q3. I want somebody to answer what is the value for Q1. Those who know, raise your hands. Usha. Q1. Yes, Usha. Q1 substitute.
C1
C1 into
V, ma'am.
V. Q2.
V.
Q2 ma.
C2 C2 V into V.
Very good. Q3.
C3 into V.
Very good, Usha. So we'll substitute it. Q1 is C1 into V, Q2 is C2 into V, and Q3 is C3 into V. Now when we are adding, what will we get? General, this is Q is equal to C into V is for the combination. CV should be equal to, instead of Q1, we write it as C1 into V. Instead of Q2, you write it as C2 into V. Instead of Q3, we will write it as C3 into V. Pooja, what is common here in this expression? C1V plus C2V plus C3V. What is common? Kirtana, Dhantakshmi.
V, ma'am.
Yes, V
V,
is
ma'am.
common. Very good. So when V is common, you can write it as C is equal to C1 plus C2 plus C3. This is in terms of your parallel combination of capacitors. So today's class we have seen three derivations. First derivation is for capacitance. Second one is for capacitors connected in series. And third is for capacitors connected in parallel. So when you go through this, if there are n number of cells, you will write C is equal to sigma into Ci. The effective capacitance will be the sum of the individual capacitances C1, C2 and C3 when you're putting it in statement. The effective capacitance in parallel combination is larger than the largest of the individual capacitances because we are adding. In series combination, it will become lesser. In parallel combination, it will become more. So this is what we are going to see about series and parallel combination. Any doubts? You have any doubts, you can just ask.